Astrophysics is our gateway to understanding just a fraction of the vast realm of space. For the brightest young minds on our planet, there's a challenge that puts their knowledge of this realm to the test. It's the International Olympiad on Astronomy and Astrophysics. Let's dive into this challenge together and see what we can learn from it. Once a year, the exam gathers students from around the world and serves as a way to encourage students to study astronomy and also fosters international collaboration. You have to be a high school student to take part, but the exam covers content you would encounter well into a university degree on these subjects. This is a copy of the 2019 exam questions. These questions cover such a broad range of knowledge that to ace it, you need to be superbly well-rounded in your astronomy and astrophysics knowledge. I was shocked to see what's near the end of this paper. It's something that sets this exam apart from any astronomy exam I've ever taken. It's not just enough here to memorize some equations and plug in some numbers. The last page of this exam is a practical test, meaning you go out at night with a telescope and have to find real objects in the sky under a time pressure and with an examiner watching you. That sounds intense. But before we get to that, let's start with a look at the theory questions. Question 1 asks for this list of 11 astronomy-related events to be put in chronological order. So what do you think came first? Some options include the discovery of the planet Uranus, the discovery of the first planetary nebula, or the first successful measurement of stellar parallax. And then what was the most recent? The discovery of the expansion of the universe, Viking probes landing on Mars, or the launch of the Hubble Space Telescope? In the answer, the first event was the discovery of the planetary nebula, and the last event was the launch of Hubble. Pause to read the rest of the order. Question 2 is about a measurement made in 1919 of starlight that was deflected from its path by a small angle as it passed by close to the Sun. The amount of deflection is said to be proportional to the mass of the Sun and the distance away that the light passes it, multiplied by a few constants. The question asks if it would be possible to detect a deflection of light that passed close by Jupiter or the Moon. To solve this, you need to recognize that the distance to be used in the formula is the radius of the body, and then compare your estimated angle of deflection against the present-day accuracy of this technique, which is 0.1 milliarcseconds. With that accuracy, you would indeed be able to see light deflected by Jupiter, but not from the Moon, as the Moon is not massive enough to bend the light a detectable amount. In 2019, the exam was held in Hungary, and you can see a local reference in question 6. It is about European satellites named Sentinel-2 and shows 2 images taken by the satellites of a chimney in Hungary, which is the 3rd tallest building in the country. One image was taken in June, near the time of summer solstice, when the North Pole is tilted closest to the Sun, and one image was taken in December, near the time of winter solstice, where the North Pole is tilted furthest away from the Sun. We are asked to tell which image is which, or as they say, which date do we expect the shadow to be longer? See if you can get it. Would the chimney have a longer shadow in June or December? The answer is December. That's their winter, and the Sun elevation is lower in winter, leading to longer shadows. This question continues on and gets harder and much more mathematical when students are asked to then estimate the height of the chimney using the shadow length. It isn't as simple as Pythagoras, and instead involves estimating the elevation angle of the Sun using a trig identity and solving a quadratic equation. There's a link in the description to the solutions document if you want to try it yourself. Other interesting questions after this one cover the effects of sunspots, the changing brightness of variable stars, finding the distance to a galaxy cluster based on the velocities of the galaxies inside it, and seeing if it would be possible to photograph a Hungarian nanosatellite from the ground before it burned up in the atmosphere. These questions are hard because they require tricky conversions between units and a seemingly impossible to remember array of various formulae and equations. The next section of the exam is more intense, as it is data analysis, with questions that more closely resemble what research astronomy might look like, sifting through observational data to find patterns. Someone who works as an astronomer would likely spend their time at a computer writing programs and processing images of stars or galaxies, often taken by other people using huge ground-based or even space telescopes. A professional astronomer could get away with never operating a small backyard telescope themselves, unless they wanted to for fun. But in this exam, that knowledge is essential, and it's actually nice to see, promoting what sometimes feels like a forgotten art. In observational task 1, you get 5 minutes to align a finder scope so that what it shows in its crosshairs is the same as what you see in the main eyepiece. Then you get 10 minutes to observe the planet Saturn. You have to find and mark the position of Saturn's moon Titan and show the orientation of Saturn's rings. I recently got a telescope again after years without having one, and relearning how to use it brought back a lot of memories for me of times when I used to do this often. I couldn't believe how many nights I had let pass without looking at Saturn or seeing the things that are right up there. You don't need a telescope to do that. You just need to be curious and willing to go outside in the cold. But having to fiddle around with a telescope forces you to be out there long enough to take notice. Inspired by this exam, I tried to complete the third task, which is observing the planetary nebula M57. Other challenges from the exam include finding a variable star in the constellation Cygnus and estimating the magnitude of two stars in the constellation Ursa Minor just using your eyes. This exam has reminded me why I love astronomy, but competitive exams do have a knack for beating passion out of people by cranking up the intensity and making the pursuit of knowledge about winning rather than about joy or understanding. I hope that the students who are lucky enough to participate in this event are able to maintain and channel their enthusiasm for the subject. For non-students, if this stuff interests you, then maybe think about joining a local astronomy club. Whole careers can be made out of astronomy and astrophysics, and not just in the ways you might expect. I'm excited to introduce the sponsor of this video, a non-profit called 80,000 Hours. They are not asking you to buy anything, they are trying to help you find a career that might change the world. The name comes from the average number of hours someone spends working in their lifetime. With all those hours on the line, it is worth devoting some time to thinking about what you want to spend your career doing. Backed by over a decade of research alongside Oxford University academics, 80,000 Hours recommends career paths with high social impact that go beyond being a doctor, teacher, or charity worker. Their advice helps you to find a fulfilling career that works for you and does good in the world. Their co-founder studied physics at Oxford before turning his attention to altruism. If you're watching my videos, you're probably interested in astronomy, physics, math, or science, and these skills are represented in many of the career paths on the website, such as software engineering, technical AI roles, biotechnology roles, and even space governance. Sign up for their newsletter at 80,000hours.org/Tibees and you'll receive a free in-depth career guide. Plus, they offer a job board with high-impact openings, an insightful podcast, and free personal career advice. It's all fully philanthropically funded. They provide some really great resources, so go and have a look at 80,000hours.org/Tibees. That link will also be down in the description.